The universe is vast, where innumerable stars are roaming along with innumerable planets. Extremely hot planets boil at temperatures of several thousand degrees. Frozen planets are too cold for life. Deserted worlds are plagued with harmful radiation. There are also planets where rock rains from the sky. The Milky Way galaxy is thought to contain hundreds of billions of stars. Between them, supermassive stars explode at the end of their life and turns either into a black hole or a neutron star, a star with a radius of only 10 kilometers but contains mass of 10 to 25 suns, highly dense and emits low blue lights. Some of these stars spin up with time and continuously emit beams of electromagnetic radiation from the magnetic poles. This radiation can only be seen when a beam of emission is pointed directly toward the observer. Such neutron stars are known as the pulsar, where the fastest one scientists have ever detected spins 716 times per second. However, it is believed that pulsars have the ability to rotate 1,000 to 1,500 times per second. And around 23,000 light-years away from the Earth, a such neutron star is carrying 3 exoplanets, humans' first exoplanets. It might hard to believe, but it took almost 7 decades after Hubble's discovery of Andromeda galaxy to detect a second planetary system. The incident took place in January 1992, when 2 astronomers were able to detect 2 planets orbiting that pulsar. Both of them are most likely tidally locked to the star, and one of them seems to have a thin atmosphere. Then a few years later, another planet was detected, also tidally locked but much smaller than the others. And despite being very close to the star, its surface temperature is -7 degrees Celsius. But how astronomers were able to detect these distant planets? And how do they even gain an understanding of the planet's atmosphere? There are several methods being used to detect distant planets. However, the method was used to identify the planets in the orbit of that pulsar is called the Pulsar Timing. Pulses of radiation from a pulsar are so regular that they are more accurate than an atomic clock. When observers notice slight regular variations in the timing of the pulses, indicate that the pulsar is moving back and forth, orbiting the center of mass of a system with 1 or more planets. Astronomers can deduce the orbit as well as the mass of these planets by precisely measuring irregularities in the timing of the pulsars. The method is so sensitive that it can detect planets as small as 1/10 of the mass of Earth. The order and arrangement of planets and other objects in a planetary system is due to the way the system forms. When a system is young, only rocky material can withstand more heat, so planets located near the stars becomes terrestrial. But the presence of such elements in the universe is quite rare, comprising only 0.6% of the mass of the nebula. Because of that, they can't grow large as like gas giants and stay small with solid and rocky surfaces. Meanwhile, the materials that we see as ice, liquid, or gas settle in the outer regions of the young system. Gravity pulls these materials together, and that's where the gas and ice giants form. But in some planetary systems, these gas or ice giant rides gravitational waves and starts to move closer to its host star. When this process occurs, if another planet in the system approaches the giant, then in many cases, its strong gravity gives extra speed to the approaching planet. Just like the help of gravity of a planet is taken to increase the speed of space probes. As a result, that planet loses its orbit and starts to flung away toward the outer space to become an orphan planet. On the other side, as the gas giant approaches its star, it starts to get hotter and hotter, where the temperatures of the planet can reach several thousand degrees. One such exoplanet was detected in 2013, where rocks fall from the sky like rain. Average temperature is 2,500 degrees Celsius, and its orbit is incredibly small now, evener than the Mercury of our solar system. Completes a year in just 1.8 days, and tidally locked with its star. As a result, the temperature of the day side is hellish, which melts even rocks, which are then driven towards the night side by the massive storms. There, temperature decreases slightly, and they turn into liquid from gaseous state and starts to fall like raindrops. However, the temperature here is not that much lower either. It's around 1,832 degrees Celsius. To get an idea of weather conditions, NASA's Spitzer Space Telescope is usually used because Spitzer does not use visible light to observe. It uses infrared, which is a part of the light spectrum that we cannot see with our naked eyes. Infrared is heat. An advantage of observing exoplanets with infrared is the ability to see radiated lights from a planet orbiting a bright star. When observing a distant planet with an ordinary telescope, the planet appears very faint because of the star's brightness, which is several thousand times greater than that of the planet. But when the same planet is viewed in infrared, the internal heat of the planet causes the planet to glow, which makes it more observable and measurable. Besides that, telescopes like Hubble and James Webb also helps to measure the atmosphere of exoplanets. When light's coming from a distant planet through these telescopes gets passed through a prism, the spectrum of light gets separated, which is much like a barcode. Scientists can read it and give an idea about the planet's atmospheric condition. Another such planet was detected in 2005, but instead of rock, it rains molten glass. And instead of storming downwards, they get swept away across the planet in 5,600 miles per hour storm surges. This planet also has a very close orbit to its star, completes a year in just 2.2 days. But despite that, the temperature of the planet is 1,700 degrees Celsius. This is due to the extended atmosphere, which blocks most of the radiation coming from the binary star. Upsilon Andromeda B, a world of fire and ice, tidally locked to its host star, completes an orbit under 5 days. Whilst the dayside temperature of the planet is 1,600 degrees Celsius, the nightside temperature in some places gets as low as -20 degrees Celsius. This is mostly due to the layer of gases located in the upper atmosphere, which reflects the rays coming from the star, and another layer of relatively cold gases located between the core and the upper atmosphere. Planets usually revolve around their star in circular orbits, but in some cases there are exceptions. An example is Pluto has an elliptical orbit around the Sun. Weird, but not so much like this one. A gas giant 3 times larger than the Jupiter, which has been observed for almost 2 decades. The orbit can be compared to the shape of an egg, and it could take 70 to 75 years to complete an orbit. As difficult as it was to observe the planet, the reason for its weird orbit was much easier to determine. A possible answer to its odd orbit is that it's an orphan planet that got shooed away long time ago from its parent star. Then at some point it got trapped in this star's attraction. And it is thought that due to such an orbit, this planet will not be able to remain trapped here for much longer either. Rather, will fling away to become an orphan planet again. The number of such orphan planets in the Milky Way is not low at all. Rather, it's believed to be 20 times more than the stars. After leaving their planetary system, some planets turns into an icy realm. Some are able to maintain their structure for a while, even its ring system like the Saturn. So far, about 70 orphan planets have been identified. But since they do not orbit any host star, it is very difficult to detect such planets. There are only 2 ways to identify orphan planets. One is microlensing, and the other is direct imaging. Microlensing occurs when an object, such as a star or planet, comes into near-perfect alignment with an unrelated star. Light travels in a straight line, but if space-time is bent, which happens near something massive, like a star, light follows the curve. Anytime 2 stars align closely from vantage point, light from the more distant star curves as it travels through the warped space-time around the nearer star. If the alignment is especially close, the nearer star acts like a natural cosmic lens, magnifying light from the background star. Planets orbiting the lens star can produce a similar effect on a smaller scale. Whilst direct imaging is the way of detecting directly, using visible light or infrared.